Welcome you all in my next lecture. So in my last lecture I talked about like maxima minima. In fact I started with a scalar field, that means you have functions from Rn to R. Then I introduced the concept of relative extremum, that means a relative or local extremum, that means maxima or minima, and of course parallelly I introduced the notion of what is called absolute or global extremum. Along with I introduced the concept of critical points, saddle points, and then I said that okay, if I have a function f nice, and suppose you have that kind of assumption that f has a maximum and a minimum, then the question is how to choose a points in the domain so that I can talk about that. Yes, so all those points my functions attains those extremum. So that is another kind of problem, I should say. So how to find those points where your functions attains those extremum, so that I am going to discuss in today's lecture. Along with, if time permits, then I will talk about the methods of Lagrange multipliers. That means there is a constraint problem, that means I would like to find something on some functions subject to some conditions, and then at the end exact differentials. So that's the tentative plan. So first I will start with, so suppose I have a functions, or suppose I have a scalar field, and suppose you have an extremum exist, okay, then how I can choose some points, or what are the point I should guess that yes, I should check only on those points so that I can talk about yes, extremum attains, because the domain might have infinitely many points. So there should be some algorithm so that I can talk about, and of course I talked about critical points. So you will see that that means there is a way to check that how to choose those points so that your extremum attains all those points. So as I said, so this is my aim, that to find the extremum points of f, that means where to look for. So that means, is there any way I can say that yes, these are the points, you have to just check and those are the points enough, you don't have to check any other points. So if you want to look for the extremum attains some of the points, so these are the points you should go ahead with that and check whether that extremum exists or not. So look, so what I said, so if I have a function f from some subset E of Rn to R, that means I have a scalar field, then where to look in E, that means what are the points in E for extremum values of f, that's the plan. So that means the maxima and minima, then I conclude that yes, look, the maxima and minima of your function f can occur only at, what are the points? You have to consider, or you have to check the boundary points of that set E, and then you have to consider the critical points. Now boundary points means what? Boundary points, if I just draw a picture, suppose this is your set E, okay, so suppose this is my E, then boundary point means what? So you can see that this is your boundary point. So I should say this is the boundary. Whatever neighborhood I can take in this point, there should exist one point in that neighborhood from the set, and there should exist another point in that neighborhood outside the set. So therefore whatever point I can take here, and whatever neighborhood, one point from the inside set, another point from the outside set. So this is called the boundary point. So that means if I have set E, suppose this is my set, then what is your boundary? Boundary is this one, okay. So in other words, in terms of, I have already discussed about interior points, closure. So sometimes you say that boundary notation is del of E, which is actually the closure minus interior. Sometimes this is also called boundary sets. So therefore, if I have a set, I have to look for the boundary points, that is first. And second one is the critical points. Critical points means what? I already said, that means if all the first order partial derivative exist, then it has to be 0 of one of the partial derivative does not exist. Now once I talked about boundary points, so what are the points remaining? All the interior points in that set. So that means if this is the boundary points I have to check, and if I have another point, this is inside it, that means it should be an interior point, okay. So that means if I want to check some points where my maxima and minima exist, that means I have to look for the boundary points, number one. Number two, critical points. Critical point means it should be an interior point of P where all the first order partial derivative exist and they are 0, and it is an interior point where at least one of the first order partial derivative does not exist, okay. So that means what are the point I should look for? First, given a set E, you have to look for the boundary points. you have to check the boundary points along with the interior points of P, which are critical points. That means if all the first order partial derivative exists at that interior point, it has to be 0, else if there is at least one partial derivative which does not exist at that point. So that means these are the points you should check, and that will give you the point where your extremum exists. For example, I have given one example. For example, suppose I am starting with a rectangle, closed rectangle. Now, what is the picture? You can easily see x running from -1 to 1, y running from -1 to 1. So, what is your set? I mean, this is my R2. So, this is my set. So, this is my -1, this is 1. I think I should say 1, 0, and this is -1, 0. What is it? This is 0, 1, and this is 0, -1. So, this is your set. Okay. So, that means now I want to find the points where it attains, suppose, maxima and minima. Of course, it attains because what is your function f? F is x square plus y square. It's a very nice function, polynomial function, right? And what is your set? Domain. Domain is that closed and bounded set, that means it's a compact set. So, that means maximum and minimum exist. Now, one can say that, okay, I now confirm that yes, maximum and minimum exist because I have a continuous functions, and wherever my function is defined in that set, it is a closed rectangle, it is a compact set. So, therefore, maximum minimum exists. Now, the question is, can you tell me the points in the domain where it attains? So, that means I just already discussed, you have to just check the boundary points along with some interior point which is a critical point. Okay. Now, boundary point means this is the boundary you have to check. These are the points. There are many, infinitely many points. Okay. But there is a kind of nice boundary. Even if it is boundary, say only if I have this one, only one component is varying, other is fixed. Similarly here, and similarly here, and similarly there. Corner point you can easily identify. So, therefore, boundary points you can easily identify what are the boundary points. And now you have to find the interior point or critical point, that should be an interior point. So, look. So, now its function is very nice. So, you just calculate del f del x and del f del y. I think you have already done it. I have done it in my last lecture. So, what is del f del x? So, your del f del x is nothing but 2x, and your del f del y is nothing but 2y. Now, since partial derivative exists at all points, so therefore, there should not exist any point where one of the partial derivative does not exist. That case will not occur here because your function is nice. So, partial derivative exists at all points. So, you just calculate first order partial derivatives, and suppose del f del x and del f del y is 0, then you have to solve it. Now, if del f del x is equal to 0 is equal to del f del y, what will imply? It will imply the point 0, 0. So, that means what are the points you have to check where my function should attain its extremum? It's only the interior point 0, 0 you have to check, or you have the boundary point you have to check. So, that is what you have to, if you check it at 0, 0, it gives the value 0, and if I take the boundary point, so that means it is actually the corner point I am talking about, plus 1 minus 1, plus 1 minus 1. If you do that, you will see that minimum will exist because it is a positive valued function greater or equal to 0. So, therefore, 0 is the kind of minimum value, so and it attains at the point 0, 0. And what about the maximum value? It should attain at the point plus minus 1, right? Either 1, 1, minus 1, 1, 1 minus 1, minus 1 minus 1, and maximum value is 2. Okay. So, maximum value is 2. So, these 4 points they attains. So, these 4 points plus minus 1, first component and second component is plus minus 1, it is actually the corner point. Okay. So, that is how. So, that means first observation is that first you have to somehow justify yourself that yes, whatever function is given and the set is given, first you have to ensure yes, maxima minima exist, and the next step is that what are the points it attains its extremum, and to check that you have to consider the boundary point and you have to consider the interior point which are the critical point. Okay. So, that is how, this is the kind of method one should go ahead to find out what are the points my function should attain its extremum. Now, later you will see this, of course, this is a kind of again boundary points, you could have many boundary points and critical points, of course, it depending upon the functions, okay, and the domain I am talking about. So, there also I can have the extremum, but now if I like ask about the very precise, not extremum, like say relative maximum or relative minimum. So, this is more precise than extremum. So, there are some certain another conditions you will see that will I will discuss in my next lecture, in fact next slide I should say. So, okay. So, now there is a necessary conditions for extremum. So, that means if I have a function and suppose extremum exists, then what can I say? So, that is called a necessary condition. So, necessary condition for extremum, that means if I have a functions or if I have a scalar field and suppose extremum exists, then what can I say? So, look at the statement very carefully. Okay. So, this is the statement of the theorem. This is necessary condition for extremum. So, what I am doing is that, so I am starting with a functions f from set E subset of Rn to R, which is a scalar field. I am saying that if an interior point x star of E is a point of relative or absolute extremum, and if all the first order partial derivative of f at that point x star exist, then it has to be 0. Okay. So, therefore, that means if I have a function and if I have a point x star which is an interior point, along with that my all the first order partial derivative, or suppose of course I should say that that point x star is a point of relative or absolute extremum, and if all the first order partial derivative exist at that point, that has to be 0. So, now interior point, what do I mean by interior point? I already explained in my earlier lectures what do I mean by the interior point. Suppose this is your set E, suppose this is my set E. Okay. So, if I take a point x star, okay, suppose this is my point x star. X star is called an interior point if there exists a neighborhood around the point x star and which is fully contained in that set. That is called an interior point. So, therefore, a point is called the interior point if there exists a neighborhood around that point which is fully contained in that set. Now, if I take a point here, okay, this is in the boundary. Now, whatever neighborhood I can take around that point, so let it be x double star, whatever neighborhood I can take, at least there are some points which is an element outside the set. That means I cannot have a neighborhood around the point x double star which is fully contained in that set. So, this is a boundary point. Okay. So, therefore, a point, it should be an interior point, that means a point of course inside the set, and there should be a distance, positive distance from the boundary, so that I can have a small open neighborhood around that point or small open ball, so that it will be fully contained in that set. That is called interior point. So, therefore, necessary condition said that if I have a scalar field, if I starting with an interior point with the fact that the interior point is a point of relative or absolute extremum of f, and along with that all the first order partial derivative exist at that point x star, then it has to be 0. That means all the first order partial derivative at that point is 0. In other words, the gradient vector of f at the point x star is 0. If you remember what is gradient vector of f at the point x star, in my earlier lecture I have done it. So, this is actually del f del x1 at the point x star up to del f del xn at the point x star, right, or in other words d1 f x star up to dn f x star. Now, all of them are 0. So, therefore, gradient vector is a 0 vector. So, therefore, necessary condition that if I have a scalar field, if I having a starting with the interior point which is a point of relative or absolute extremum of f, along with the fact that all the first order partial derivative exists at that point, then all the first order partial derivative at that point has to be 0. In other words, gradient vector of f at the point x star is 0. Further, it says that the directional derivative of f at x star in all direction is 0 provided my function is differentiable. So, that means earlier one I assumed that existence of first order partial derivatives at the point x star. Now, I am assuming little extra or little strong condition, which is that f is differentiable, that means total derivative exists. Now, if the total derivative exists, then of course directional derivative exists, and of course in particular partial derivative exists. And if you remember, I already proved a theorem, if my function is differentiable, then the directional derivative of f in some directions can be written in terms of the partial derivatives. Now, if my function is, if I assume that my function is differentiable, that means directional derivative I can write in terms of partial derivatives, but already said that necessary condition said that if the point is a point of relative extremum or absolute extremum, and since the partial derivative exists, it has to be 0. So, that means directional derivative of f at that point x star can be written as the combinations of partial derivative at that point, and all the first order partial derivative at that point is 0. So, therefore, directional derivative is 0 any direction, and that exactly I have written, okay, because I assume more strong condition like f is differentiable, that means total derivative exists at the point x star. As a corollary, again it follows from there that if I have a functions f, say scalar field, if an interior point x star of p is a point of relative absolute extremum of f, and f is differentiable, this is a very strong condition, right, and if f is differentiable, then the derivative also is 0 map, and it's okay. Why? Because if my function is differentiable, and then you know that what is the derivative, it should be a linear transformation, right, and you can write explicitly in terms of the partial derivatives. If you remember, derivative of f at x star, which is nothing but, because derivative is a linear map, because f is a function from where to where, f is a function from E subset of Rn to R, okay, then derivative then derivative at the point x star is a linear transformation from Rn to R. That means it should be a 1 cross n matrix, that means a row vector. And what is that vector? You know, this is the vector. If you recall my earlier lectures, it should be actually d1 of f at x star up to dn f at x star. That is the gradient vector of f at that point. Now, I already said that if my x star is an interior point, and if suppose at that interior point is a point of relative or absolute extremum of f, and since all the first order partial derivative exists, it has to be 0. Now, each of the component is 0, so therefore derivative is a 0 linear transformation or 0 map, and that's exactly I have written. Okay. So, this is the necessary conditions. So, that means necessary conditions, always be careful. I am talking with a point x star, I should say that I am starting with a interior point with the fact that it is a point of relative extremum, along with the fact that if all the first order partial derivative exists, then it has to be 0. So, that is the necessary condition. Okay. So, now I come to the new concept, what is called quadratic forms. Okay. So, now you may say that, okay, how that quadratic form certainly came into the picture. It has a connection actually, because you see I am starting with a scalar field, and I am trying to say that, okay, if the extremum exists, what are the points I should look for, so that I can talk about that extremum attains at that points. Now, since I am starting with a functions or scalar field, then I already discussed the existence of total derivative, and if you remember, I already discussed there is a notion of what is called Hessian. Okay, what is Hessian? If I have a functions from Rn to R, then you have to consider the gradient of f, it is a map from Rn to Rn. Okay. So, if I have a functions f from Rn to R, then is the gradient is a map from Rn to Rn. Okay. Now, if I talk about, suppose gradient, again it is a differentiable map. So, therefore, I can talk about the Jacobian matrix of the gradient at some point, and it is an Hessian. And if you remember, there is a connections between the double derivative. If my function is twice differentiable, there is a relations of the twice differentiable or double derivative of my f at some point in terms of the Hessian. And Hessian, if you remember, if I assume that my function is say suppose second order partial derivative exist and they are continuous, if you recall that Hessian matrix is symmetric matrix. So, now the point is that to talk about or to identify some points where my local extremum in particular relative maxima, relative minima, or global or absolute maxima minima exists at some point, and what are the points. So, then you will see that since I am dealing with a scalar field, the Hessian matrix, later on I will talk about that, Hessian matrix plays a role to find out those points, or to talk about that, yes, those are the points where my functions has a relative maxima or relative minima. So, that is why Hessian came into the picture. And Hessian, what is Hessian? If I assume my function is very nice, then it is a symmetric matrix. Now, if I have a symmetric matrix, then of course, the associated, you can associate a quadratic form. So, that is how it come into the picture. So, that means it is actually interlinked. That means it is not just arbitrarily came into the picture, that quadratic forms, because later on you will see when I will identify the points of extremum, or what sort of points of extremum, like whether it is relative maxima or relative minima, there Hessian plays a role. Okay. And in terms of Hessian, quadratic form will be there, and there are some certain concept I will introduce, like positive definiteness or semi definiteness. Using those conditions, you will be able to conclude, yes, if these things is true, then I will say that at that point relative maximum exists, or relative minimum exists, or absolute maxima, absolute minima exist. So, that is why I need to introduce the notion of quadratic forms associated with a symmetric matrix, and then couple of notions I will introduce, like positive definiteness or semi definiteness, and later on I will talk about that, yes, if I have a matrix or if I have a quadratic form, and then if this thing satisfies, then there will be a conditions on the second derivative of your map, and with that conditions I can conclude that existence of local extremum or global extremum. Okay. So, that is why quadratic form came into the picture. So, now what is quadratic form? So, I am starting with a symmetric matrix. Now, what is symmetric matrix? I already discussed. Our matrix is called symmetric if H is equal to H transpose. A transpose means, that means what? It is row and column interchange, that is the transpose. So, H is, capital H is symmetric, means Aij is should be exactly Aji. So, that means the matrix is exactly equal to its transpose. That means the element should satisfy these properties. Aij should exactly equal to Aji. So if I start with the symmetric matrix n cross n, a function q which is a map from where to where, x is capital X is what? It's a element in Rn, right? So that means q is a map from Rn to R. So given a symmetric matrix, I am associating a map q which I am calling as a quadratic form, which is a map from Rn to R. And what is the action? Action is q acting on x is nothing but x transpose hx, whereas x transpose is a point in Rn whose component is small x1, small x2, small xn. Now look, so this is an element in R, you can say easily, right? Because what is h? H is n cross n matrix. What is my x? My x is n cross 1 element, okay, n cross 1, sorry, n cross 1, okay, because x transpose is 1 cross n, so x is n cross 1, and what is x transpose? It is 1 cross n. So now in the matrix multiplication, this is get exhausted, this is get exhausted, so end up with 1 cross n element, and which is an element in R, right. So therefore q, so given a symmetric matrix, I am associating a map q which is a map from Rn to R, which action is q of x is equal to xt hx, where xt is an element in Rn. This is called a quadratic form or a bilinear form. Okay. Let us see some examples. For example, if I take q is a map from R2 to R, so q is a map from say R2 to R. Okay. What is map? So q of x1 x2, so this is my xt x1 comma x2, this is my matrix, symmetric matrix, because you see off diagonal term they are equal, b by 2. So if I just take compute this object, then what will happen? This one. This is one of the examples of a quadratic form. Similarly, if I have a map from q, say from R3 to R, so this is again perform the same calculations, you will end up with this is a quadratic form in R3 to R. So if I have a symmetric matrix H true cross 2 symmetric matrix, it will be a quadratic form like that. If I start with a symmetric matrix H in 3 cross 3, that means this symmetric matrix, you see this is the diagonal, you do not have any restriction, and off diagonal should be equal. So this is off diagonal, this is same, this is same, this is same. Okay, that means Aij is equal to Aji. So therefore it is a symmetric matrix, and this is the corresponding quadratic form. Some more properties. If I have a quadratic form, what are the properties? First properties is that for any quadratic form q acting on 0 vector, it has to be 0, and it is crystal clear from the definition, because what is your definition? Q of x is equal to xt hx, right? Now if x is 0 vector, that means 0 transpose h 0, h is a linear transformation acting on a 0 vector, it will give you 0, you forget about that one. So this is straightforward. Second one is a quadratic form this if I have a H which is an identity matrix. In particular, identity matrix is a symmetric matrix, I will have associated quadratic form, and what is that quadratic form? So if you just replace here xt identity x, then what will happen? This is xt x. So that means this is a row vector and this is a column vector. Then what will happen? So this is a row vector, that means x1 x2 xn, and this is a column vector x1 x2 xn. Then what will happen? This is nothing but x1 square up to xn square, and which is same as norm of x square. Now that's exactly I have written. Okay. Another property is that if I starting with a point ei whose ith component is 1, rest of them are 0, that means it is in the ith coordinate axis, and if I have a symmetric matrix H, then this is useful actually, later on you will see. Okay. So what is that? It says that you just evaluate, that means what is this? This is nothing but, you can say that this is nothing but q of ei, right? This is q of ui. So q of x is nothing but xt hx. So this is nothing but q of, okay, you can say that this eit, I should say, yes, in terms of this notation. Okay. So this is the action. So action of q on eit, which is nothing but ei h eit, and which is nothing but the ii element of h, and this is straightforward you can do, because this is your h ij matrix, right? And what is ei transpose? Ei is a row vector, so ei transpose is a column vector, right? 0 0 0 1 0. So that means at the ith position, this is ith positions. So what will happen if I take the 1? So it should be like what? So the first element should be h1i, second one is h2i up to hni, right? And then you have to hit it with ei in the left. So that means this is, if I hit it by ei, so that means what? This is 0 0 0 1 0 0 0. So there is only this ith position, right? So, only if I multiply this with this, only ith element will survive, that means this will be HII. So, these properties will be useful in my next slides when I will talk about, so given a matrix, if something happen in the diagonal, then I can talk about it is easily satisfy some notions like semi-definiteness. Okay. This is some properties of quadratic forms. Okay. Now, this is the classification. So, that it's needed to talk about again for the existence of extremum, or to talk about when or if some points extremum exists, whether it is a relative maxima or relative minima. So, those kind of things that I will talk about later. So, first before that I should talk about classifications of quadratic form. So, now quadratic form I have defined. So, I am starting with a symmetric matrix, I am associating a quadratic form, few examples I have given and some properties I have discussed. Now, this is the classifications. It says that if Qs is strictly positive for all x is non-zero, then I will say that is a positive definite. If Qx is negative for all x non-zero, this is called negative definite. If Qx some point Qx is positive and some other point it is negative, then Q is said to be indefinite. Okay. Positive definite means it should be strictly positive for all x non-zero. Negative definite means it is strictly negative for all x non-zero. Indefinite means at some point x it is positive, at some point x it is negative. And if Q does not satisfy the top three conditions, there are any of the first three conditions, then I am saying that it is actually semi-definite. So, that means first, second and third it should not be satisfied, then I will say that it is a semi-definite form. Does not satisfy means what? That means, so look, the first one it says that it should be strictly positive for all x non-zero. Now, the question is, if there exists a non-zero x such that phi x is 0, then what can I say? So, that kind of situation will arise. So, that is why I am saying that it is semi-definite. In particular, in case of semi-definite, if Qx is positive for all x, then it is a positive semi-definite. Now, what is the difference between positive definite and positive semi-definite? Positive definite says that for all x non-zero, your Q of x should be strictly positive. However, in the case of positive semi-definite, the question is that for all x, Qx is greater or equal to 0. That means, it might happen there are point x which is non-zero, but Q of x could be 0. So, that is what it is, that is what is happening here actually. So, that means positive definite means actually I am talking about strictly positive, or positive semi-definite means I am talking about non-negativity, that is it. So, these two things are different, strictly positive and non-negativeness. So, positive definite means strictly positive, and positive semi-definite means I am talking about non-negative, yes, non-negative, yes, that means it should be greater or equal to 0, positive, yes. And in particular, if this is non-positive, that means Qx is lesser or equal to 0 for all x, then I am saying that is a negative semi-definite. That means, what is the difference between negative definite and negative semi-definite? Negative definite means whenever x is non-zero, your Q of x is strictly less than 0, but in negative semi-definite, there are some point x could be non-zero, but your Q of x could be equal to 0. So, that means non-positiveness will be there. That is the difference between negative definite and negative semi-definite. Negative definite means strictly negative, and negative semi-definite means it is non-positive. So, that means Qx is lesser or equal to 0. That means there could be some point x non-zero, Qx can take a value 0. Okay. So, then I have pointed note here, it says that all the above terms used to describe the quadratic forms Q or classifications of Q can also be applied to the corresponding symmetric matrices. Now, what does it mean? I am saying that, okay, how I define the quadratic form? I am starting with a symmetric matrix, then I am associating a map Q, I am saying that it is a quadratic form, and then I am saying that, okay, if Q satisfies this, then these are the things happen. So, what I am saying is that instead of if Q satisfies these properties, then I can also say that H is also, like if I say that if Q satisfies Qx is greater than 0 for all x is non-zero, I am saying that Q is positive definite, I can also say that H is also positive definite, because whatever I have defined in that Q, I can just replace Q by H, because I am getting Q from the matrix H. So, that means there is associations. So, with the symmetric matrix I am having the quadratic form. So, that means I have a classification of quadratic forms, and that classifications I can replace Q by my matrix H, then I can also say the same thing. That means if Qx is strictly positive for all x non-zero, then I am saying that Q is positive definite, or also I can say that H is positive definite. Similarly, if Qx is strictly less than 0, for all x is non-zero, I am saying that Q is negative definite. I can also say that your H is, the symmetric matrix H is negative definite, and so on and so forth. That is the relation. So, all the above terms used to describe quadratic forms Q can also be applied to the corresponding symmetric matrices, because actually quadratic form and symmetric matrix, they are associated. Starting with the symmetric matrix, I am having the quadratic form. Few examples I have given, very simple example. Positive definite means, one example, Q of x1 x2 is equal to x1 square plus x2 square. Now, from the definition you can see, if x1 x2 is non-zero, it is always strictly positive. Just taking the minus sign, minus of x1 square minus of x2 square, again x1 x2 non-zero is strictly negative. Indefinite means x1 square minus x2 square, that means at the point 1 0 it is positive, at the point 0 1 it is negative, so therefore it is indefinite. Positive semi-definite, you can just take x2 square, so therefore this is positive for all x. So in other words, I can have a point x which is non-zero, but still the evaluation is 0. Consider this point, whose second component is 0 and first component is 1. So that means 1 0, if I take this point, so if I take, this is my point x, which is a non-zero point, and what is the evaluation of Q of x, which is nothing but, since second coordinate is 0, that means x2 is 0, so this is actually your x1 comma x2, which is x. So x2 is 0, that means Q of x is 0. So I have the existence of a point, non-zero point, but still the evaluation is 0. Similarly, negative semi-definite, this one. So of course this is always negative, less than 0, and there are some non-zero points where it is actually taking the value 0. So these are very simple examples of positive definite, negative definite, indefinite, because it is taking both positive values, both negative values in some points, and then you have a positive semi-definite, negative semi-definite. They are very simple examples of a quadratic form. Okay, so just as I said, this evaluation I talked about that. So there is a theorem that when I can say that I have a symmetric matrix which is indefinite. So this theorem, what is the statement says? So let H be a n cross n symmetric matrix. Okay, suppose your symmetric matrix has at least 2 main diagonals. So that means this is my matrix, right? So what are the main diagonals? H11, H12, H. Okay, so what is my matrix? It should be H diagonal. Given this matrix, what is the diagonal elements? H11, H22, H33 up to Hn. Okay. So what it says is, the statement says that if I have a H, okay, and it has at least 2 main diagonal entries are of opposite sign. Okay, suppose H11 is positive and H22 is negative. Okay, whatever, any. So you have a H11, H22, Hn, right? If any 2 of them are opposite sign, then the matrix H is indefinite, or I should say that because it is symmetric matrix, the corresponding quadratic form is indefinite. So what is the definition of quadratic form indefinite? That means at some point it should take some positive values, at some point it should take negative values. Proof is very easy. So what I am doing is that, okay, for I from 1 up to n, because I am in n dimension, so therefore consider the coordinate vectors or basis of this n dimension, that means Ei, whose ith component is 1, rest of them are 0. And I already said that if I have a symmetric matrix, this properties is true. Ei H Ei transpose is nothing but Hii, right? And then 2 diagonal elements, what is the hypothesis of the theorem? It says that any 2 of diagonal elements, if they are opposite signs, suppose Hii and Hjj, 2 diagonal elements, and they are having opposite signs. And as I said, what is this object? This is nothing but Q of Ei. Right, or in fact I should say Q of Ei transpose, I should say, right, Ei transpose, this Q of Ej transpose. It's up to you how I am thinking about is a row vector, because I am writing Ei as the row vector. So therefore I am writing whether Ei or Ei transpose doesn't matter, right? I mean, you can write it Ei, because I am saying that Ei is the vector 0 0 0 row vector, right? So that is what I am getting. So I am a symmetric matrix. So I have this observation earlier, and Hii and Hjj, 2 distinct elements, they are having opposite sign. That means the corresponding quadratic form evaluated at Ei taking positive. If it is positive, then Q of Ej, it should be negative. And if Q of Ei is negative, then Q of Ej is positive, and that is by definitions. If I have a quadratic form, at some point it is taking positive values, at some point it is taking negative values, then it is indefinite, and hence the corresponding symmetric matrix is indefinite. This is very example, you just say this is the diagonal elements, it is positive sign, it is negative sign, and therefore it is indefinite. However, I should add a point that converse of the above theorem is not true. That means if I have a symmetric matrix and if I know in the diagonal elements at least 2 elements occurs with the opposite sign, then of course that matrix is indefinite or the associated quadratic form is indefinite. But suppose you have a matrix, symmetric matrix H, and suppose you do not have any this kind of things that use all the diagonal elements are positive or all the diagonal elements are negative, then what can I say? Can I say that is it always positive semi-definite or negative semi-definite, or is not indefinite? What sort of conclusion I should say? So is that okay, even if your diagonal you could not have any control that if it is taking the same sign, then also it is indefinite even though your diagonal entries are all positive. That means converse of this theorem is not true. That means of course if I have a symmetric matrix, if you look at the diagonal, if any 2 diagonal elements having opposite sign, then you can immediately say it is indefinite. However, if I have a symmetric matrix and in the looking at the diagonal you cannot conclude anything, that means all are taking same sign, still the matrix could be indefinite, or the quadratic form associated with the symmetric matrix is also indefinite. So that means the converse of the above theorem is not true, and this is the corresponding example. So look at the diagonal, they are having same sign, positive signs, and this is symmetric. But if you just check that this matrix or the associated quadratic form, this is indefinite. That means you can have the existence of 2 points where q acting on one point it is taking positive value and q acting on another point it is taking negative values. Okay, so I think I should stop here. So then in my next lecture I will talk about the classifications of quadratic form, few examples I have talked about, and then I said that since the symmetric matrix associated with quadratic form, then you can replace the quadratic form, the classification, by symmetric matrix. But now the natural question is, okay, since I am having a matrix, that means already I introduced the notions of definiteness, semi-definiteness. Now since I am dealing with matrix, it is expected, okay, matrix means I can talk about eigenvalues. In terms of eigenvalues, can I talk about the definiteness? Answer is yes, you can. I think in my next lecture I should talk about that. Okay, thank you.